Hello class, so this is CSE 5250, Section 1, uh, Week 5, Spring 2023. I hope all of you are keeping yourselves warm over throughout this week because the weather's been insane. Cold weather, hailstones, snow up in the mountains, and that's gonna continue that's probably gonna continue for at least the next week, so stay warm. But other than that, I hope you had a good President's Day weekend. I saw no point in having a video up for which our meeting would be 2 weeks after that. So there wasn't a video for last week. I will be picking off where we left off last week. No, last video, where where I was about to talk about thread safety. The easiest way to understand thread safety is this: each thread has to do something specific, and it cannot. Each thread does something with a specific piece of data, and no other thread is allowed to work on the same data as any other thread. So, if thread, if one thread has to work on a specific element in an array, no other thread is allowed to work on that. Though, if you remember operating systems, it can be a little bit more nuanced. It might be a little more nuanced than that. By that I mean, is it okay for multiple threads to read the same thing from memory at once? And in comparison, is it okay for more than one thread to try to write to the same thing at once? I can tell you right now that the answer for the latter is no, it's not okay. You're gonna get race conditions if you do that. So that's the one thing we want to avoid when we're doing anything related to parallel programming. And that's why synchronization exists. It's why we have mutex locks. Those things enforce that only one thread is allowed to be doing some atomic operation at a time. Atomic meaning we cannot break the operation apart into anything smaller. Speaking of which, atoms in physics, it was thought that those things would not break apart into anything smaller, but then those things broke apart into something smaller, and then those parts broke up into something smaller. I guess it still makes sense in a chemical context. But anyway, we don't want threads to step on each other's work, so to speak. So, with that, let's go back to our example of matrix multiplication and see what's going on here. So if you recall from the last assignment, I instructed you to write two things. The first one was a hello world program using OpenMP. The second one was a dot product function. No, it was a program that calculated the dot product of two vectors. And if you recall from the video I put up about dot products, yeah. Anyway, the product of two matrices is basically a matrix whose entries are dot products. When we did the dot product program for programming assignment 1, you will have noticed by now that each thread is getting two numbers to multiply, and then they're going to increment some value with that product. But remember when I said about two threads trying to read, no, two threads trying to read from the same thing versus write to the same thing? That is the point. That is where we need to introduce synchronization. Specifically, one thread at a time can can increment this value that's going to be the product at a time. So, basically, each thread calculates a product between two numbers, and then they have to wait their turn to increment this running total that's going to be the dot product itself. So one thread at a time, increments at a time. Yeah, one thread at a time. So this matrix multiplication program is basically going to be nearly identical to the dot product calculation that we had in the previous assignment. By that I mean, instead of doing one dot product and having that result be stored in a variable, we're going to do an entire matrix's worth of dot products, and each result, each dot product, is some entry in the matrix itself. So the very first entry is going to be the first row vector dot product with the first column vector of the second matrix. So matrix 1's row vector multiplied with matrix 2's, right, let me do this again. So the very first entry in the product matrix is going to be this row vector multiplied by this column vector. If you're wondering how I did that, I highlighted a whole column. I pressed down Alt while I was selecting. So it's basically a rectangle select. See? Anyway. Now, there are a few special properties associated with the matrix multiplication. That involves, is there a matrix that if you multiply it by another, if you have a square matrix, is there a special matrix that you can multiply it with so that you get the same matrix out? Is there some matrix where matrix M times that matrix is the same matrix M? The answer is yes. It's the identity matrix. This is a matrix that's full of zeros except for this diagonal of ones. So what this program does is it's going to, we could do this example using any two matrices. You can go as far as to write a random number generator for these, to populate these matrices. In this example, I painstakingly wrote out all these numbers myself. You don't have to do that. Spare yourself the trouble. Anyway, for this example, I have it so that we're multiplying this matrix with an identity matrix so that the product matrix will be the same as the first matrix. We do that using a triply nested for loop. And where I left off was we have the innermost for loop be parallelized. Now, I'm not sure if I talked about this yet, but you can imagine unfolding an entire for loop. So if I had an even more basic for loop that looked something like this. If I had a really simple for loop like this, what this does is replace the same line of code being repeated 1,000 times, but with a different number each time. And each number is gonna be like what, 0 to 999? Anyway, you can imagine unfolding a for loop like that. But if it's a nested for loop, you have to unfold the innermost for loop and then unfold the next for loop that contained that inner for loop, and then so on until you've unfolded the entire for loop. And when we do that for this for loop, you realize there's like, what, 1,000 multiplication operations to do? Yeah, so it's 1,000 multiplication operations, but a specific group of 10 multiplications are going to be added together, and then that's going to be stored as some value in the product matrix. So, with that visualization of unfolding a for loop in mind, when we introduce multithreading, what happens is those for loop iterations get divided up by however many threads there are. When I run programs on my computer, by default, unless I tell it otherwise, it's going to default to 16 threads. However, here I have it so that, no, I have 10 by 10 matrices, so what happens is it's only going to use 10 threads at a time. Because in the extreme case, we have, in the extreme case, we would have one thread for every for loop iteration. Is this peak efficiency? Food for thought. Anyway, if we had fewer threads and like a lot more for loop iterations, we would just roughly divide up all those for loop iterations into roughly equal parts. If you had like 1,000 for loop iterations divided among, say, 3 threads, it would roughly divide the for loop iterations into 3 roughly equal pieces. So one of those pieces is actually going to get 334 loop iterations, while the others get 333. It's going to be something like that. So in my case, where I only have, to calculate the dot product of 2 vectors of size 10, it's just going to give one multiplication operation to one thread. So only 10 threads are needed. And then those threads have to wait for their turn to increment the value that's going to be the dot product. Okay, so the innermost for loop is parallelized, but what does that look like? Well, it looks like this. We start with this matrix here, it's multiplied by this matrix here, that's the identity matrix, and we get the same matrix as before. Okay, but what if I did this? Does this work? Remember, thread safety says whatever work a thread has, it cannot do any other work that another thread has. So, no stepping on each other's toes. Okay. So what does this say now? Okay, so we're gonna iterate through each row of the first matrix. We're gonna start with the first row of the first matrix. But now we've parallelized the second for loop. This is the one for iterating through the columns of the second matrix. So what's happening now is this. This first matrix's row vector is being multiplied by each of the column vectors all at once. By that I mean we're calculating 10 different dot products at the same time. Is this okay? Well, what happens now is each for loop is going to get, each for loop iteration of the second for loop is going to have its own for loop here. So what happens is this. Each thread is doing its own for loop calculation, and it's going to multiply two numbers one at a time and then add that and then increment some value. So k belongs to this for loop here. This k belongs within the scope of this for loop. The I and j, the j belongs within the scope of this for loop, and each thread, you can think about it like this. Each thread is going to calculate every possible j. And then the I is, well, given to us already, because we're stuck in the first for loop iteration. It's going to do one row at a time. So every thread is going to have the same I. Every for loop iteration is going to have a unique j. And the k's are going to have, each thread is going to have its own set of k's. Hopefully that makes sense. But anyway, it turns out what's going to happen is it's going to do the same thing as before. So these k's, k equals 0 to k equals 9, they belong to each thread. They have to, by that I mean, each thread is going to have its own k equals 0 to 9. Maybe I'll just show you. The same thing as before. So yes, this works. 2147, 971, So this. By parallelizing the second for loop, we are able to. So previously we had this. We would do individual multiplications one at a time, and then increment some value that's going to be the full dot product. Here, we're doing individual dot product calculations, but only one row at a time. Is it possible for us to have it so that we have a thread for every entry in the matrix? So, you get a thread, everyone gets a thread. Can we do that? It is in theory possible, but we would have to rewrite the two outermost for loops into being one single for loop. It would look something like this. It would look something like this. We would have dot product 1, dot product 2, dot product 3, dot product 10, dot product 11, 12, 13, 14, 15, 16. And dot products 1 through 16, because my computer is like this, 16 threads, it would calculate 16 dot products at a time. So, in the first step of this entire calculation, the entire first row and part of the second row will be calculated all at once. And then it would advance to the next 16 after that, and after that. And then we'd calculate the entire, dot product. No. All the dot products that constitute the entire matrix product. it gets a lot more interesting when we get into NVIDIA CUDA because we can do something like that. But anyway, getting a little off the rails, so maybe it's a good time to show you what your next programming assignment looks like. So, this one is going to consist of 3 parts, but 2 of the parts are really closely related. The first part is to write a matrix multiplication program using OpenMP. So, you're gonna want to make a triply nested for loop and make one of the for loops parallel. You could also go the route of enumerating. No, you could also try to go the route of having a doubly nested for loop, and one of the for loops just iterates through the entire array, row by row. So, in some cases, you have to pretend that. What I'm trying to say is, sometimes you have to represent a 2D thing as a 1D thing. But when you do so, you have to do some special conversions between a one-dimensional index to what's basically a two-dimensional index. So one number has to translate into 2 numbers. Anyway, to make things simple, just you have a triply nested for loop, make one of the for loops parallel. So that's the first assignment, and it's basically exactly what as I've shown here. The second assignment is going to be a little more fun. Yeah. Part 1 is the matrix multiplication. Part 2A and 2B is a little more fun. We're going to write a program that calculates Pythagorean triples using nested for loops. You may have heard of. There's a good chance you'll have heard of this, and it says a squared plus b squared equals c squared, where we want a, b, and c to be whole numbers. Yeah, if you hear about Pythagorean triples, they're typically whole number solutions to a squared plus b squared equals c squared. I will say this right now, there are special functions out there that given 2 values, they're usually a u and v. Given those 2 values, it will calculate a Pythagorean triple of a, b, and c. Now we could do that, and that would work too. But suppose we didn't have that knowledge, and all we had to go by was brute force. So, I'll show you what that would look like later. But that's part 2A. For part 2B, and this is where it gets a little more fun, we're going to modify the Pythagorean theorem by doing this. We can either add a times b or subtract a times b. So this part is only worth 5 points. Basically, are there integer solutions for this weird form of the Pythagorean theorem? So yeah, that's your next programming assignment. When we meet on Monday, I want to talk to you about how long would it take for you to do this assignment. Because I can I'll put the instructions up on Canvas, but I don't want to put a due date yet unless I know for sure how long would it take for you to do this assignment. Right, so I showed you part 1 so I gave you a good walkthrough of part 1 already. Part 2, let me just erase all of this for now, and let's take a look at part 2. What do we mean by a Pythagorean triple? How will we find a Pythagorean triple anyway? Well, it's simple. It's going to be something where a times a plus B times B equals C times C. And the hint is to use a triply nested for loop, basically. Actually, no, it doesn't say that at all. It just says nested for loops. But we have three variables, A, B, and C, so we may as well just use a triply nested for loop. So let's do that. Int A equals 0. Let's do something small, like 100. A plus plus. There we are. C++. And then we can include an if statement in here. If A times A plus B times B equals C times C. If that condition is true, we can print out the triple itself. So it will look like this. Pythagorean triple found. %I, %I, backslash n, and then I'm gonna pass in A, B, C, and that line of code. Run. It works! But I coded it so it starts at 0. If you imagine you had like physical rods of like lengths 3, 4, and 5, you can easily make a right triangle out of that. But if you had side lengths of 4, 0, and 4, is that really a triangle anymore? 404 error, triangle not found. No, it wouldn't be a triangle. It would be just what you would have is something that's indistinguishable from a singular line segment, even though it's two segments somehow in one on top of the other. So, exercise for you is to just exclude all of these trivial solutions that involve zeros. So check this out. We have 345 and 435. The order of the first two numbers doesn't really matter, so maybe this is another exercise for you, on top of excluding all the trivial solutions. Can you write your program in a way that it excludes duplicates of solutions? By that I mean, if you have a 345 triangle, it's going to be the same as a 435 triangle, because it literally is. It's just flipped the other way. So that's just another exercise for you. Try that if you like. But anyway, that's going to be your next assignment. Your next assignment. For your next assignment, we're gonna cycle back to the stuff of Eratosthenes. So I tried this out a little earlier. So let's take out that pragma and try this out now. So I added a few more modifications to this code from the last time you may have seen it. Mainly, it's really not that much different, okay? Anyway. So what we're going to do is we're going to time how long it takes for the code to execute. We're going to do that by we're going to include chrono. We're going to add using namespace standard chrono to save our fingers. So when we get our execution times, we're gonna want to get the current time at the start of the program, and then the current time for when the program ends. We find the difference between the two, and that's going to be our execution time. So code consists of this, and then these two lines of code. And between the start and the stop, it's going to be the program itself. So as a reminder, the step of Eratosthenes goes like this. We're iterating through an array of numbers from 1 to our search max. If we encounter a prime number, if the outer for loop encounters a prime number, we're going to start an inner for loop that's going to cross out the multiples of that prime number. So if we start at 1, we're gonna break the whole thing. Because 1 divided by 1, every whole number is divisible by 1, so we can't start at 1. So I have to cross that out. We denote, for our purposes, we denote non-prime numbers as being replaced with zeros. So this is going to start as an array with all the numbers from 1 to the search max. We replace 1 with 0 to say, hey, this number wasn't prime. And then we go on to the next number from there. So 2 is the next number. So we start at 2. Hey, this is probably a non-prime number. So we're gonna start at 2. And we're gonna enter a for loop where we cross out all the multiples of 2. One way to do this was to have a for loop iterate one element at a time. So it's going to go to the tree, ask itself, is this number divisible by 2? And if it isn't, it's going to leave that alone and go to the next number. That would be the number 4. It's going to ask itself again, is this divisible by 2? The answer is yes. It's going to cross out that number, replace it with 0. Then it's going to go to the next number, 5, and then 6, and then 7, and then 8, and so on, until we've crossed out all the numbers. That is a slow way of doing it. But it's a little bit easier to understand when you consider, with a for loop like this, it doesn't matter the order in which you cross out the numbers, because we have that modulus operation. But does it matter the order for the outer for loop? It turns out yes, because the outer for loop does this. It's going to go to the next prime number based on whatever numbers it has already crossed out. So it can't skip ahead to the number 5. When we run this, we can't start at 2 and then skip to the number 5, because 3 is in the way and 4 is in the way. 3 is not a problem, but 4 is, because that's a number that's a non-prime number. It has to cross out all the non-prime numbers for each multiple that has encountered. It's going to cross out prime numbers for multiples of prime numbers for all the prime numbers it's going to encounter. So it has to first cross out the multiples of 2, and then 3. And because 4 would be crossed out by then, it would skip the number 5. So we can't just do the outer for loop in any order we want. We can try, but would that be efficient? But I can tell you right now that it is theoretically possible to do the inner for loop in any order, so that is the one we want to make parallel. So if you imagine unfolding this entire for loop into like 10 million different loop iterations, we can stop and realize we can do this in any order and make it parallel. But I wrote this a little bit differently though. And here's how it's different. let's say we're crossing out the multiples of 3. Yes, let's say we're crossing out the multiples of 3. It's gonna start at 3, but it's gonna go up by 3 to the next number after that. And then cross that out. And then 3 numbers after that, cross that out. 3 numbers after that, cross that out, and so on and so forth. Hold on. So yeah. Let's just run the program now and see what kind of execution time we get. If we're going to search for prime numbers up to 10 million. What do we get? It took us 4.9 million microseconds, about 5 seconds to find all the prime numbers. Press any key to continue. Okay, so it worked. But let's make it parallel now. Will that work? So it turns out this thing has no critical sections. When we cross out numbers, we're replacing them with a 0, so it actually doesn't matter if a number was already crossed out. So the number 6 was a multiple of 2 and a multiple of 3. When we cross out the multiples of 2, 6 will already be crossed out. But when you get to 3, it'll be crossed out again, but it doesn't matter because it's already been crossed out. So, does that hurt the program in any way? Again, food for thought. Okay, so let's run this now. If you recall, it took us 5 seconds to run it without parallelization. Expected something. Expected a for loop. Okay. I put it in the wrong place. It has to go before a for loop. That took 5 seconds. Here, it took us 4 seconds. So not much of a time decrease. But that might be because we actually have 2 for loops here. One of them is to populate the entire array full of numbers. So, would it make any difference if I changed the code here so we didn't have a pushback operation? Because if we tried to make this parallel using parallel for, we might have a race condition because of pushback. I'm gonna rewrite this little bit of code I'm gonna pause the recording, rewrite this little bit of code, and see what we get. Okay, so I rewrote the code a little bit, and this is what it looks like now. There's many ways of declaring a vector. One of them is to give it a size and an initial value for all those values. So here I'm just initializing it to a vector full of zeros of size search max, and then I'm gonna need that for loop to populate each number in the array. Would this be any different? Remember, the baseline was 4 seconds. Now it's 2 seconds. So here's the weird thing. Depending on how you write this program, you might have some other inefficiency slowing you down. Okay, but what if we did this? Since this itself is its own parallelizable operation, we can make this parallel also. And now it takes less than 2 seconds. So yeah. However we program our sieves, we want to be consistent about how we do our time, about how we get our execution times. So, in my case, it wasn't enough to parallelize the inner for loop that's part of the sieve itself. To get real speed up, I also had to parallelize the for loop that filled the entire array full of numbers. So yeah. But now I kind of screwed up the execution time comparisons, because here it was 2 seconds with this parallel for loop for filling the vector full of numbers, while it was 5 seconds for when we had no parallelization at all, and this is declared using pushback. So, I'm going to set this thing's thread count back to 1. I need that OMP library. Include omp.h. I'm going to force this thing to be 1 thread. OMP set num threads 1. I'm gonna force it to be 1 thread and see what we get now. It was 5 seconds using pushback. Now it's 3 seconds without pushback. So now it takes 3 seconds with this thing without pushback and no parallelization. If I ramped it up to 16 threads, which is what my computer will default to, now it takes 2 seconds. A little under 2 seconds. So yeah, however we do our data collection, we want to be super duper consistent. We want to be consistent. By that I mean, we want to use the same program, but change the thread count. So, from one... Yeah. For one, we cannot have like different code for each thread count setup. So, in my case, I had to parallelize 2 separate for loops to get any significant speed up. Or I had to get a noticeable speed up. Anyway. But yeah, however you choose to program your sieve, you want it to be the same. You want it to be the same code for both getting the execution time and setting the number of threads. So yeah. So this is gonna be part of your next assignment. Your next assignment, which doesn't have a due date yet, I have to talk to you about that, is going to be matrix multiplication and a little bit of fun, Pythagorean triples. That information will be up on Canvas. When we meet together again next Monday, I want to talk to you about how long it'll take for you to do that assignment. And also, I'm going to talk to you about, I want you to talk to me about any issues that you have with getting your programs to work, and so we can see if we can debug that. Okay, so when we get around to doing this, what we want to do is eventually what we want to do is have a table of execution times. So for one, we want to change the core count. We want to change the thread count to see what benefit having more threads. We want to see what benefit having more threads has. But we want to see whether those benefits help for larger search max. So this is 10 million. I could go as far as 1 billion. If I did that, it stops working. So maybe let's not do that. Maybe let's go one order of magnitude lower and see how long this takes. When we do this benchmarking, I want you to go as far as your computer can handle. That took 18 seconds to find prime numbers up to, what, 100 million? Yeah, 100 million. And that's with 16 threads. If I did this with 32 threads, if I just up the thread count without any consideration as to how yeah, I upped the thread count to 32 and it didn't really help. But that was because my computer can only do it can only execute 16 threads at a time. I do have another CPU, but I haven't put it in my computer yet. My computer is currently a 8-core 16-thread CPU. My computer has an 8-core 16-thread CPU. I have in a package a 16-core 32-thread CPU that I have yet to put into my computer. And as a sort of science experiment for myself, I want to see if that has any benefit. How many threads can I throw at a computer before it starts, before it starts to enter the territory of diminishing returns? You're going to do something similar to whatever extent you're able to do so. So if you have a 4-core 8-thread CPU, you're going to want to test... If you're limited to a 4-core 8-thread CPU, then test all the way to 8 cores. For me, I have an 8-core 16-thread CPU, so I would be able to test up to 16 threads. Again, it's going to vary based on your computer. We're not really benchmarking against each other. We're not really testing against each other's computers. Rather, we're testing against our own computers. So the only two variables in this experiment will be the thread count and how far are we searching for prime numbers. So that's what we're going to do in the following weeks. So I'm going to end the video now. And when we meet up again Monday, we're going to talk about how long it'll take for you to do the next assignment and any other issues you may be having with getting anything to work. Right, so that's it for the video. Hopefully I'll see you on Monday. Stay safe, stay warm, stay dry. Tread with caution up in the mountains. Right, see you next week.